everyone. Today we're going to talk about energy and specific heat. So energy is the ability to do work. So let's zoom in here. So chemical and physical changes involve changes in energy. We've been talking about the difference between a chemical and a physical change. A chemical change, you rearrange the atoms, and in that process, you often get things that are new substances and you can't get back your original stuff. So you rearrange the atoms and you form new stuff. So we saw this in our chemical versus physical change activities, and we could see it with a chemical reaction. But even without a chemical reaction, you can look at a particle diagram and see that those atoms are rearranged and they're touching new things. A chemical change would be like burning. Another example of a chemical change we saw was rusting. Physical changes, on the other hand, you still have the same stuff. Before and after, you have the same thing. So a physical change would be like boiling or heating something. So in these processes where we have either a chemical or a physical change, energy is either absorbed or released. So we have energy either absorbed or released. And usually that happens in the form of heat or light. And sometimes also sound accompanies these. But think about, for example, the methane that gets burned on your stove. So if you have a stove that you see fire on at home, then it burns natural gas, which is methane. And the natural gas burning gives off light, so you see the light. And then it's obviously hot, right? That's what the stove is for. So we can talk about energy qualitatively, as we're discussing right up here, but we can also talk about it quantitatively, and for that we use the variable Q. So with Q, we can talk about energy being transferred as a result of temperature difference. Heat is always transferred from a hot thing to a cold thing. You can't transfer cold, you can only transfer heat. So you can see in this image that heat is being transferred from the hot thing to the cold thing. Also, heat is not the same as temperature. Heat is not the same as temperature. So think about this example. If you had a spoon that had boiling water in it, so there's our boiling water, and a mug that had boiling water in it. Remember, boiling water is 100 degrees Celsius. And you had to pick which one got poured in your lap, which obviously we would never do. That would be terrible. But if you had to pick, you would obviously pick this guy over here, right? Even though they're the same temperature. The temperature of both of these is 100 degrees Celsius. That's really hot. But you still have a preference about which ends up in your lap, because the one that has the smaller quantity has less heat to transfer. So heat is not the same as temperature. These two things are the same temperature, but this one has more heat and this one has less heat. And it has to do with the amount of matter is present, which makes it an extensive property. Heat must be extensive because it deals with the amount of matter present. So here's how we do these calculations. We need an equation, and so the equation we're going to use here, we call it Q equals mc delta T. So let's look at each portion of that equation. So the first part, Q, we already said that Q stands for heat, and the unit that we're going to use to represent that is going to be joules. We saw that on our conversion activity. Another unit you can use for this is calories. We don't use that as often in chemistry. The next quantity that we look at is mass, and we've used mass a number of times, like density equals mass over volume. The unit that we're going to use here is going to be grams. Now the next one is new. Specific heat is our value C, and the units of that are going to be joules per gram degree Celsius. We write that like this, but we know it actually means joules in the numerator and grams degrees Celsius in the denominator. Sort of like density was grams per milliliter or grams per centimeter cubed. So that's the specific heat. So specific heat is a new value for us, probably one you haven't heard of before. And it tells you how well something holds on to heat. For example, water does a really good job holding on to heat. Water specific heat value is 4.18 joules per gram degree Celsius. But many things have a much lower value. Water's is very, very high. So for example, aluminum has a specific heat value of 0.9 joules per gram degree Celsius. So that's a really small value. That means that it's pretty easy to heat aluminum up, but it also cools down very easily. Another example that I like to give for this is the difference between water in something like hot chocolate or tea or coffee and toast. You probably burned your mouth before on something water-based like hot chocolate or tea or coffee, but you probably haven't burned your mouth on toast. Well, water only gets up to 100 degrees Celsius. At 100 degrees Celsius, that's hot enough to burn your mouth. Now, toast, on the other hand, gets actually hotter than that, but it cools down so fast that while sometimes you might have burned your fingers on it, you probably never burned your mouth on it, because by the time it got to your mouth, it had cooled down enough so that sometimes even it feels cold. Toast kind of gets cold right away. That's because it does not do a great job holding on to heat. It has a very low specific heat value. Let's try a problem together. How much heat is given off if 387 grams of copper at a temperature of 205 degrees Celsius is cooled to 115 degrees Celsius? The specific heat constant for copper is 0.385 joules per gram degree Celsius. The equation that we're going to use is Q equals mc delta T. We should always start by writing down our equation. Next, we should plug in our values with units. So our mass is 387 grams. Our specific heat value is 0.385 joules per gram degree Celsius. And then you have to read the problem to make sure that you're putting the final temperature first. It says that the object is cooled to 115. So it ends at 115 degrees Celsius and it started at 205 degrees Celsius. The first thing I'm going to do is the subtraction. When I subtract 115 minus 205, I get negative 90. And then I'm going to do my multiplication. When I type this into my calculator, my answer is 13409.55. My units are going to be, I'm going to cancel grams and cancel degrees Celsius, and then my units are going to be joules in the end, which makes sense because that's what we are supposed to have for heat. And I can also round this answer. Because this number only has two significant figures, my rounded answer is 13,000 joules. So my answer is 13,000 joules. If you want to leave your number unrounded, that's totally fine. This is an acceptable answer as well. Let's do one more problem together that involves a little bit of algebra. It says, what mass of water is present if 340 joules changes the temperature from 20 to 25 degrees Celsius? Once again, we are going to start with the equation Q equals mc delta T. At this point, you could plug your numbers in and then solve, or you could solve and then plug your numbers in. Most people are more comfortable with plugging numbers in first. So that's how I will show you how to do it first. If you stay till the end of the video, I'll show you the other way to do it as well. One strategy that you can use to solve a problem like this is to identify all the parts of the equation in the word problem before you plug them in. See, I've written them above the places that they are in the problem. When I plug my numbers in, the value that I'm missing is the mass, which is what the question is asking for. However, I have all the other numbers that I need. Again, I'm going to start by doing the subtraction, which is going to give me 5 degrees Celsius for the difference here. Now I can multiply my C value and my temperature change. And I'm keeping track of my units. However, if you ignored them, you would still get the same value, and you can look back at the original equation and what units you are supposed to have to figure out what they are in the end. The next thing I have to do is isolate m. In order to do that, I'm going to divide both sides by 20.9. In my calculator, I get 16.2679, blah, 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 a whole bunch of other things, grams. If I'm following the rules for significant figures, I can round this to 16 grams, and that is my mass, which is the answer. So another way to do this problem is by doing your algebra first. We know that we're trying to solve for the mass, so we can solve for the mass first algebraically and say that Q divided by C delta T equals M C delta T divided by C delta T. Basically, I took the other things over here and divided both sides by them so that I could get them to cancel. That means that our mass is equal to Q over C delta t. So we know our delta t is going to be 5 degrees, and we can plug that in there. And then we can plug in q and c. And when you solve and round, you'll realize that you get the same answer you did before, because we did the same math that we did before. But this is just one other way to do it. It's up to you whether you'd like to plug in and then solve, or solve and then plug in.